the recording thing. Perfect.
Very
All
good.
right. Well, thanks everybody for joining us for the November our Govys seminar. And before we started the recording, we were talking about snow, so it's interesting. I'm getting things in the chat about various states and cities that have had snow. So far in Virginia, DC area, it is not snowy. I don't think it's cold enough yet for snow, so we'll see. But Ted Enamorado is our speaker today, and I'm super excited to have him with us. And he's in St. Louis, as you can see by his slides, and it looks like it's sunny behind him, but he said it's a little bit cold there, so maybe the snow hasn't gotten to you yet. Anyway, Ted is going to, he's one of the, I guess I could say one of the developers, right, of the fastLink package for record linkage in R. And so he's going to give us, I guess, kind of a tutorial overview of the package and give us some spoilers, I guess, for what's coming soon in the next version of FastLink. So this is, again, one of the sort of episodes, I guess, in our series of seminars on record linkage. So we're very happy to have Ted here. He said he's willing to answer questions as we go. Hopefully that's true, right, Ted? I got that right? Okay, good.
That is totally correct.
Okay, and I'll monitor the chat and the Q&A, so you could put it, in either place, the questions you have, and then if it's a question that I think can wait, I won't interrupt you, Ted. But if it's something urgent or a point of clarification or something, then I'll interrupt you. So as usual, we let the speaker introduce themselves. So I'm going to pass the microphone to Ted and let him tell us a little bit more about him and about FastLink. So thank you again, Ted. I'll go off camera and pass it to you.
Thank you, Wendy, and thanks everyone for being here. So it's a great privilege for me to be chatting about something that I feel really passionate about, like you guys, on how to integrate information from multiple sources in a very challenging scenario where we lack a unique identifier that links records across dataset, right? So, as Wendy mentioned, my name is Ted Enamorado. I'm an assistant professor at Washington University in St. Louis. I'm in the political science department. And for the past, I'll say, yeah, almost like 10 years now, I have been working on record linkage, first out of necessity because I wanted to answer questions that require merging large administrative records when you lack a unique identifier. But then, out of necessity, I realized that the tools that I had available to me at the moment were like not enough, or like were not going to give me answers in real time. So then I started worrying a little bit because I needed to produce a dissertation. So then I worked and tried to investigate why like the tools that we had available at the time, even though like we're basically on the very same type of models, did not scale for large data sets, right? And then with collaborators now at Harvard and my other collaborator is at Facebook, then we created the R package FastLink, and we have been, for the past 7 years, I have been the main maintainer of FastLink and developer as well. Okay. So let me motivate the talk a little bit. So I hope that everyone can see my slides. So I prepare a few slides.
I can see them, so it's good.
All good. So let me start from the beginning. How is that I started my journey on record linkage? So to give a little bit of perspective, I'm a social scientist. And one big question in political science more generally is that, well, like when we tabulate, for example, self-reported turnout in a survey like the American National Election Studies, ANES, we see that people self-report that they voted at least 70% of the time, if not more, right? But on election day, if we were to calculate actual turnout, so the turnout of all the individuals that are eligible to vote on each given election, we see that in the best case scenario, in the 2008 election, at most 60% of people say that they actually voted. But then we see that there is a large gap between self-reported and actual turnout. And then there has been a big debate in the literature in political science about what can be the culprit of this. So some people blame that it's over-reporting. So people claiming that they voted while in fact they did not. And why is that? They blame social desirability bias. So when you're like survey out and then you're being interviewed and you are being asked about whether you voted or not, people try to appear to be good citizens, so they go with the likely answer, even though they didn't vote. So that's one valid answer on what valid mechanism of which we observe like this really large gap between self-reported and actual turnout, so the gap between the red line and the black line. But then there is another group of scholars that have said, actually, like, I don't think it's over-reporting this. I think it's a problem of sampling likely voters. What happens is that surveys, public opinion surveys like the ANES and the CCS, widely popular public opinion surveys in political science, what happens is that these surveys are conducted before and after an election, and the turnout question is asked in its most part after the election happened, right? So it's trying to go after the behavior after the election, but it happens that, well, like the survey is conducted in two waves out of the problems with attritions in surveys when you try to collect panel data is that you lose a lot of respondents. And then what these scholars say is that what is happening here is that when moving from the pre to the post-election, even if you start with a sample of eligible voters, what you might end up with is a sample of likely voters in the post-election survey, because those are the people that are more willing to participate. So if you end up with a sample of likely voters, then there is not a surprise. If people are not over-reporting, then not surprisingly, we can also end up with a high turnout rate among those individuals because those are likely voters, right? So two plausible explanations for this question, right? But it happens that with polling, it becomes a big thing whenever an election happens. We just had an election a few weeks ago, and then everyone that is trying to predict elections, they use numbers that come from self-reported turnout and the self-reported preferences in who they are going to turn out for. And then this is the main inputs for the predictions. And then we see that if that information is incorrect, then the predictions are not going to be as accurate as we want. So how do we adjudicate the culprit of this problem? Well, like, then we have to, this is the question that I was interested in, like try to say, well, like, is it a mix of the two? Is it over-reporting? Is it a sample of likely voters? So what I had to do back in the day is, well, this problem, if you were to convince a survey like the ANES to give you access to the de-identified data, then this is a problem of just merging a survey with a voter file, because in the voter file, we have the actual turnout, in the survey, the self-reported turnout, and then we can make the comparisons between self-reported and actual turnout. And this process is called turnout validation. Actually, surveys like the ANES and others, they conduct turnout validations after the fact. But usually what has happened is that these turnout validations have been conducted by companies, by private companies that do the record linkage process for them, for a profit. So then we don't have a clear idea what are all the calls that they make when they declare a pair of records to be a match or not, right? The most important issue here is that if you want to conduct a turnout validation like this, then you have to merge datasets without a unique ID. So we'll have to resort to a second best case scenario where we will use the information in common between the datasets, right? We're going to use information like names, addresses, and age to conduct the merge. The big question is going to be how. In social science, until very recently, is quite popular. Deterministic methods were the way to go. For example, exact matching, we're going to declare to be matches only the pair of records that have the exact same values and the variables in common. Why is that this approach is so popular? Because it controls against one type of error that we might face when we are conducting record linkage, right? False positives. So we're going to be really conservative in what is that we declare to be a match, because it has to have the exact same information, or it has to be almost the same. What is the problem with that? We know that if there are typographical errors in the information in common, or there is missing values, then we'll have to, exact matching is not going to be enough. So then we have to be more flexible in how we do use deterministic approaches. It also has, I have to say, like, it's not only that it controls against false positive, it's also quite popular because algorithms on how to conduct exact matching or variations of exact matching are really fast and easy to implement, okay? And this type of ideas have real world consequences. In the state of Georgia, in 2018, they used something that it was called like the exact match law, basically for the gubernatorial election, for the midterm election of 2018. And the gubernatorial election was the culprit of that election. So there was the most visible election that year in Georgia. But it happens that in Georgia, the electoral office required that the information in the social security card or the DMV data, the license information, had to match exactly the information in the voter registration record. And more specifically in terms of names and addresses. But if you take a name like Ted Enamorado, which would be like the information that appears on my license, because they cannot fit Hispanics, especially when you come from abroad, the name convention requires that we use two last names. So my actual name is Ted Enamorado, so my last name repeats. Then it comes to the fact that I went to the DMV office in New Jersey, and then I said like, oh, like I want to get my license. And then they told me, oh, like that, there's a problem with your name. We cannot fit the two last names. We can only fit one. So in my license, my name is only Ted Enamorado. But then in my social security card, my name is Ted Enamorado, because there is no character restriction there is no character restriction order. So then if you were to try to match the two pieces of information, then you will get that Ted Enamorado using exact matching is not the same as Ted Enamorado, even though the first 12 characters are exactly the same, right? And it happens that in 2018, many campaigns in Georgia, especially on the Democrat side, they and other advocates against this type of laws, they figure out, and they accounted for at least 53,000 records that failed to match exactly on the first name and last name. And more importantly, this 80% of these 53,000 records came from racial minorities. In the case of Georgia, basically mostly from African American. And if we think that in political science it's well understood that African American voters are more likely to vote Democrat, then you are disenfranchising basically a Democrat stronghold. Okay, so this is to say deterministic methods, they have real world consequences, right? Real life consequences. So are there any better approaches? And this is where like probabilistic methods that have been widely used in statistics, computer science, and now in social science have become readily available. And why is that we like probabilistic record linkage or probabilistic models of record linkages? They're more robust to typographical errors, right? From the get-go, they were designed such that when we make comparisons, those comparisons have to be fuzzy. So we're going to allow some flexibility in how we compare names, addresses, the string value variables. Not only that, since the very early models, they are designed to control error rates. So we're not going to be just conservative on one front against false positives, but also against false negative, declaring pair of records to be non-matches while in fact they refer to the same individual. What are going to be the challenges, or like the challenges that I faced when I was trying to conduct a turnout validation for the ANES in 2016? Scalability and accuracy. What do I mean by scalability? As the data sets become larger and larger, in 2015, 2016, open source implementations of R packages and Python libraries available back in the day did not scale. That means that our dataset become larger and larger. It took more time and computational resources. So it was impossible to conduct such a merge in my laptop. Not only that, another problem that probabilistic record linkage models face is that they tend to be over-optimistic. They think the models, when you record the parameters of the model and you try to assess how much error there is surrounding these methods, they tend to be over-optimistic. So they think that they're making less mistakes than what they're actually making. And that's a piece of information that you learn as a researcher. Like you conduct a merge. After conducting a merge, some pairs of records are being declared to be matches by the probabilistic model. Then you check. You can use like heuristics, like random spot checking, check here and there what is going on with the data that you match, and then you realize that you match pair of records that do not refer to the same entity. So then, in that case, the researcher has learned this information. How is that we can create methods that can interact with these probability methods, and actually from the information that we have learned, we can pass it to the probabilistic model so that those errors are taken into account, and perhaps that information that you have learned to be incorporated into the merging process. So those are like the big challenges, and I have been working on both of them for the past few years. So this is just a slide to say like how is a probabilistic record leakage workflow, the typical probabilistic record leakage workflow. So we have two datasets A and B. In these settings, because we don't know whom is a match to whom, we're going to make a lot of comparisons in the framework that I'm going to be talking about, which is the standard approach of probabilistic record linkage. We're going to make comparisons, and those comparisons are called agreement patterns. So for a pair of records, we're going to make comparisons, and we're going to create a vector that is going to recollect the history of similarity levels across the variables in common. And then we're going to pass that information to the probabilistic model. So the probabilistic model is going to adjudicate for every pair of records in the cross product between two data sets, where that pair of records is a match or not. Okay. So let me present like some notation. So we're going to have two data sets, A and B. These data sets, as I said before, we're going to resort to a second best case scenario because we lack a unique ID. So we're going to use the fields in common. So there have to be K uppercase, where K has to be larger or equal to 1. But the more fields that we have, the merrier. And then this is where like the computational problems come about. Because we don't know whom is a match to whom, we have to compare all the records in dataset A to all the records in dataset B for every variable in common between the dataset, right? So if you have two datasets of 10,000 records each, that means 100 million comparisons per variable in common. And if you have 5 variables in common, that means 500 million comparisons, right? 500 million comparisons is a lot. So you can think, and those, when we think about the type of problems that we face, datasets of 10,000 records each, at least in social science, now that we have access to administrative records of many sorts, like voter files that have 180 million records, so then that's a very small dataset. How is that we're going to make these comparisons for every pair of records for each variable in common? So we're going to use this function that is called an agreement value, gamma Kij. So gamma is going to be the function, K referring to the K field in common, and I for record in the ith record in dataset A, J for the jth record in dataset B. And basically we're going to take, let's say we have two datasets, we're going to grab the field name, we're going to get the names of, let's say, the first record in dataset A to the 10th record in dataset B. We're going to compare the names. We're going to say, oh, like this is Ted, this is Ernest. Do they have anything in common? So we're going to use a string. For example, those two variables, what they have in common, the names are strings. So we're going to compare them using string similarity measures. And then after the fact, that's going to be a continuous comparison. We're going to convert that continuous comparison into a discrete one. And we're gonna say, well, like the comparison of Ted versus Ernest is either an agreement, is it similar, or is a disagreement? In this case, most likely a disagreement. Why do we move from a continuum version to a discrete one? Basically, in this model, think about it from a computational perspective. If you have a continuous variable, you have to keep track of many more values than if you were to just have 3 mutually exclusive values. And that's gonna get us a lot of, when I was starting working on this problem, this was my first realization. It happens that if I have 3 mutually exclusive categories, and then my model only needs to know the pair of records that are in one of these 3 baskets, then if I know the pair of records that are in the first basket and the second basket, I already know which pairs of records are in the last basket. And it happened that the disagreement is the basket that has the most records. So if I keep track of the first 2 baskets, then I don't need even to store information about the last basket because I already know who is in that basket already. So then after making that realization, then I realized, oh, like I don't need to do an expand grid of the sample space. I just need to focus on these 2, the agreement and the similarity levels. But again, like this, keeping track of just 3 values, or if this is flexible, you can do 3 values, you can do 5 values, you can do 7 values. But again, why is it super useful? Is because of computational. It's going to be more computational efficient than try to work with continuous variables. But there has been lots of work done. For example, Becca Storz at Duke, she has done a lot of work where like she works with agreement value functions that actually are modeled as if they are continuous, okay? Once we have gotten an agreement value for a pair of records for the kth variable, we have to do it for all the k uppercase variables in common. So first name, last name, and let's say address and age. Then we construct this vector that is called an agreement parent, which is going to tell us the level of the history of similarity levels across the variables in common between the datasets. Okay. So here, one example, we can pick 2 records at random. When you take a look at this pair of records, we know that they have the first name is the same, the last name is almost the same, but there is a minor typo. And if you look at your keyboard, the next letter to an H is a J to the right, right? Then we have age. These 2 records are 1 year apart, and that might be just a reflection on what is the endpoint that we're using to calculate age. And then we see that there is a more pronounced typo in the street name. Devereaux, who appears to be correctly spelled in the first data set, but then in the second data set, there are like more prevalent typos in the second data set. So we calculate an agreement pattern. In this case, the names are the same, so that's considered an agreement. The last names, there is a minor typo, so then we're going to consider that as an agreement, using, for example, Jarrow-Winkler as the measure and setting cut points. For example, if you were to use Jarrow-Winkler, and you can renormalize Jarrow-Winkler to be between 0 and 1, so 1 measure similarity and 0 dissimilarity. Then, for example, using 0.92 has been a cut point. Anything that is above 0.92 has been considered a good cut point for agreements between 0.88 and 0.92 for similarity. That's the case of a street name. And equality, it's also considered an agreement because that would be a Jarrow-Winkler distance of 1 when renormalized between 0 and 1. And then for age, for example, you can use the absolute value of the distance, the L1 norm, to take the difference between these 2, which are 1 year apart. And then you might say, well, like if the 2 records are 1 year apart, then we're going to be considered that an agreement. Why is that? Why is that not such a crazy idea in terms of border files information? You can modify these rules, right? In border files, for example, it happens that if an individual, the day and month of birth are not reported, commercial vendors of border files, they replace that information, that missing information, they fill that out, those values with the first of the month. And if the month is also missing, the first month of the year. So that's where, like, if you work with border files from commercial vendors, January the 1st is the day where, like, most people are being born. Well, like, we know that if we know anything about the date of birth of individuals, if you were to plot the distribution of date of birth across a year, it's pretty uniform. People have little say on where the day that they are born, okay? And why this task is going to be difficult, because for a pair of records, like, we can add the two pair of records and actually we can construct the agreement pattern, but then we have to do this for all pairwise comparisons. And in this case, in this simple example, we have two data sets, so that's 4 pairwise comparisons. But this is going to be the computational bottleneck. As our data sets become larger and larger, then it is going to be really time consuming. To illustrate that, here, what I have plotted basically is in red. What we have here is the current version of fastLink. So in the x-axis, we have 100, 200, 300. So that's the size of the data sets that I was using to illustrate the runtime comparisons. 100,000, 200,000, up to 600,000. So that means 2 data sets of 600,000 records each here, 2 data sets of 200,000 records each here. So when I started working on this, I was using the record linkage R package. And to merge 2 data sets of 50,000 records each, if I remember correctly, it took 22 hours, right? But then I was trying to match a survey like the ANES, 4,000 respondents, with a border file that has 180 million records. So that was many, many more comparisons if compared to that very simple example that took almost a day to complete. Then, how do I fix that problem? First, what we have in red here is the runtime for fastLink, the current version that you can download from CRAN. That the key to make fastLink fast is we're using hash tables to store the data. Basically, we have for every pairwise comparison. So when we're constructing the agreement vectors, we're going to have these hash tables. And these hash tables, we're going to record all the. So we're going to have an adjacency matrix. We're going to have, like, all pairwise comparisons recorded in that adjacency matrix. That's the thought exercise. Of course, like, the hash tables are a simpler object than that. But then we're just going to store the values for which we observe an agreement and a similar value. And then we're going to leave as zeros the sparse value, the value that is actually observed the most, the disagreements. And using that and other tricks like reverse data structure, so we're going to use, actually, we're not going to compare every name that appears in the data set. Well, every repeated mention of a name. So, for example, what happens with names when you have a large data set, if you were to tabulate the names, what happens is that some names are quite popular, right? So Ted might not be as popular, but there are other names like Joseph that is going to be more popular. So then the names repeat. But why do I need to compare all the Teds, all the Wendy's, all the dogs in one data set to the other, instead of just comparing one instance of Ted, one instance of Wendy, and one instance of dog, and variations of that? So we use what we call reverse data structure. So we have the names are going to see, but every unique instance of a name is going to serve as buckets. And then for every unique instance of a name, we're going to save all the indices of the records that in each one of the data sets that actually fit that name. So we're going to know Ted, well, observation 1, 3, and 27 of data set A have that name. And then observations in the other data set, we're going to know that Ted, as a reverse data structure, appears in records 3, 20, and 127, for example. And we're going to do that for every name. But then, because name repeats, last name repeats, then that's going to make the problem to become smaller. And that's why, like, with fastLink, to merge 2 data sets of 50,000 records each only takes a couple of minutes. Of course, scalability is still a problem. Like, if we were to try to use fastLink with 2 datasets of 600,000 records each, it takes a few hours. So it takes more than 6 hours to conduct that merge. Well, now I have been working, this is new results that I'm showing actually for almost the first time to an audience. What I have been working with the support of an NSF grant that I just got is using locality sensitive hashing techniques to make fastLink faster. So what I'm doing now is for every, so one way to reduce the problem, you might be quite familiar with this, is blocking, right? We have the problem, and to make this problem scalable, for example, we're gonna compare just males to males, females to females. We're gonna look for variables that actually are not discriminatory in terms of information. So then we're gonna use those to conduct blocking. So we're gonna just make comparisons, males to males, females to females. What I'm doing instead of trying to construct those subsets ex ante is try to do sort of, you can think of this idea of mine using locality sensitive hashing is for every field in common, what we're going to be doing is that we're not going to restrict the sample space. The sample space is going to be the same, but we're going to create, when we're comparing names, we're going to create these buckets where like we're going to put in the bucket names that have a high probability of being similar. Right? So we're going to put all the Teds, all the Theodores in the same bucket. And then we're going to go to the other bucket and it's going to have all the Annas, Annettes, names that are similar, and then so on and so forth. And when we create these buckets, this is going to be a decision of the researcher. The buckets are going to be created in a principal way. That's how locality sensitive hatching works. The buckets, within the buckets, these buckets are constructed such that the probability that a pair of records in that, the pair of names in that bucket are have a high similarity score is close to 1. And across buckets, the probability that they are dissimilar is also close to 1. So we want to maximize the within bucket similarity and maximize also the across bucket dissimilarity. So we want the records. So then we, by doing this sort of blocking within every variable in common, but still comparing in the thought exercise, comparing everyone to everyone, we are trying to do that in a more principled way than just trying to do a standard blocking techniques. Okay, so there is a probabilistic principle in that. So there is a question, is this the M running on the hash grouping? So this is where I'm going to talk about that after I present the model, Dakota. Just give me a second, okay? But I have your question. I acknowledge your question, okay? So what is going to be the model that we're going to, now that we know how to make comparisons, right? So this is all about making comparisons. Once we have made the comparisons, what is the data that we observe are the agreement patterns. What is the data that we don't observe is the matching status, the binary indicator match, not match. The Feleghi-Sonter model, what it does is basically try to model this binary indicator that we don't observe. Based on the data that we observe for every pair of records, which is the agreement patterns, how we model that is a mixture model where the binary indicator is modeled as if it comes from a Bernoulli distribution, where this parameter lambda is going to have a nice interpretation, is going to be the overall probability of finding a match across all the pairwise comparisons that we make. So it's going to be a really small number. Computationally, that's tricky because computers don't like to work with very small numbers. But then this is where the model becomes, the Feleghi-Sonter model becomes really flexible, is that because it's a mixture model, every pair of records represented as an agreement pattern is going to allow to come from the set of not matches and from the set of matches according to two distributions. And these distributions are going to be discrete type of distributions because the comparisons that we make it take only a discrete number of values, right? So we can think of multinomials where we have the number of groupings in the multinomial is going to be determined by the number of where we do binary comparisons, agree, disagree, or, for example, trinary comparisons, agree, similar, disagree. and they are going to be governed by different set of parameters. So every pair of records is going to be allowed to come from the set of matches and from the set of non-matches. We're going to use the EM algorithm to recover the parameters of the model. And coming back to Dakota's question, so Dakota's question is, how do we recover the parameters of the model now that I have used this hatching technique that creates like these buckets that basically allows us to focus just on comparisons that puts inside the buckets comparisons that are basically the same. So that doesn't change what we are thinking of Pelleggi-Sonter, because the thought exercise when we create these buckets is that they still like within the buckets we're going to make the comparison. So within the buckets are going to be the agreements and the similars, and across buckets is basically any pair of bar comparisons across the buckets is going to be considered a dissimilarity. But still, that is going to speak to the whole sample space. And why that is still like, why that doesn't affect or would not affect parameter estimation as much, because these buckets are created in such a way that we maximize, for example, the probability that we're not going to miss similar records within the bucket, and then across buckets, because the records are dissimilar across buckets, then that with high probability, those are disagreements. Of course, like there are going to be errors that we can make by doing that, and I totally acknowledge that. But then, because you control the error rate, so that's going to be a decision of the researcher, how willing is the researcher to allow for mistakes, for example, to include inside the bucket pair of records that are dissimilar, or across buckets have records that are similar and should have been in one of the buckets. So that's because those probabilities were, one idea is to let those probabilities to be close to one. So then we're trying to minimize as much as possible those type of errors, right? Of course, they can happen. To the extent that they happen a lot, then I'm totally, so to be completely transparent, to the extent like the data is super messy, and then like constructing these buckets is not a good idea because the data is super messy, then in that case, then making the usual comparison, everything against everyone, as in the traditional version of fastLink, then that's going to be the best approach to go. Okay, but once you recover the parameters of the model, and based on the information in common between the data sets, the data that you observe, the agreement patterns, then you're going to recover this parameter as this is coming from the E step, which is going to be the probability of finding a match, which is our probabilistic statement of the binary indicator, right? And we can do that for every pairwise comparison. So now we're going to have basically a score between 0 and 1 that is going to tell us how confident we are that a pair of records is a match versus a non-match. Pair of records in the blue area, the model is going to predict them to be non-matches. In the red area to be matches, and in the purple area, basically the model is flipping a coin. One advantage since the work of Lahiri, it has been that we can use these probabilities to, for example, if we're interested in running a regression on the match data, we can use those probabilities to account for the uncertainty of the merging process. And in social science, that has been quite important, because usually what we did back in the day, or what happens with deterministic methods, is that you conduct a merge, but then you take the merge as given, and then you just go and move as if the merge didn't matter, and then your regression results are not affected by any noise from the previous stage, the merge. With these probabilities, at least you get an assessment of and a way to incorporate noise into post-merge analysis, okay? Now let me talk to you about, now that we understand the model and we understand how we make comparison, one problem that I have been working on, greatly supported by the NSF, a recent NSF grant that I get, is to try to push for this idea that when we conduct probabilistic record linkage, right? And when we use fastLink, when we use SPLink, or like we use big match, basically we have to make this commitment. When we're making comparisons, we have to say, oh, like if I'm comparing string value variables, I'm gonna use Yarrow-Winkler, I'm gonna use Yarrow, I'm gonna use a distance, but I can only use one of them. And then if everything is based on Feleghi-Sonter, then we have to discretize the variables, right? But then one idea, think about this problem. Like you have in one data set, the data set is noisy, so it comes, one data set becomes enamorado Ted. So the last name first, the first name second, and then in another data set, you have Ted, enamorado, enamorado. If you were to compare the Yarrow-Winkler score, the renormalized one, where 0 is dissimilarity and 1 is similarity, that gets you a score of 0.59, okay? So that means that if we set a cut point of 0.88 or 0.80 for similarity, then a pair of records like this for first name is going to be considered dissimilar. But then the idea is like, but if you take a look at the very first 9 characters, well, very first 13 characters, including the comma and the space here, there are like minor disagreements. Basically, like the only disagreement in terms of characters is the comma and that there is not a comma here. But other than that, Ted is here, enamorado is here. Can we have a commitment where like, like we don't have to trust Yarrow-Winkler as much in this case and use other information, other similarity measures for strings that are actually more robust to this type of error, right? Why is Yarrow-Winkler so low here? Because Yarrow-Winkler it's just character-wise comparison, but more importantly, the characters are the same, so that's not going to hurt Yarrow-Winkler. What hurts Yarrow-Winkler is that Yarrow-Winkler puts a lot of emphasis in the first 4 letters of a name, of a string, right? So then my idea here is like, and this is something that I have discussed with people working at the Census Bureau in the past, and I'm sure that people at the Census Bureau has played with it a lot as well, is that what if you get an aggregator where like you compare not only using Yarrow-Winkler, but you use cosine similarity based on unigrams on like every character of the frequency of characters in a string. You use Jacquard, you use Levenstein or the deep distance. Many of them, they are correlated, at least Levenstein, Jacquard, and Yarrow-Winkler are highly correlated, and cosine has some similarity to them as well. What if we were to aggregate the information? And then we can think about like, well, but there are many ways on how to aggregate information. We can use conjunctive measures. So like, for example, we can use, let's take the minimum value. Or we can use disjunctive measures. Like, well, let's take the maximum value. But there are other methods. For example, we can take an average. One way of taking a weighted average is just to give equal weights to each one of these similarity measures. But there are other measures of how to calculate the weights. And I'm going to discuss this more thoroughly in a paper that I'm writing these days. You can use the fact that these measures are highly correlated, use the distributions of the similarity measures that you calculate to try to inform the weights and try to say, Yarrow-Winkler should be the one that gets the more weight because, for example, Levenstein and Jacquard provide basically the same information. So you can let the data speak based on the distribution of the data. But then you can be super conservative, you can be less conservative, or you can take a middle of the ground approach. But my claim here is, and I'm going to try to convince you a little bit with preliminary evidence that that's the case, that aggregating makes much more sense, especially when you are working with noisy data. If you are working with records that are really clean, for example, border files where the names are really clean, and you're working with data from a survey company where the names of the survey participants have been really collected with protocols that require for the people to have for the survey company to have actual names because they pay with checks individuals that participate in the surveys. So then in that case, it might be not, if the name conventions and the way that the names are structured is the same, there is not gonna be it's not gonna be as useful, the aggregation, but it's not gonna hurt in any case. Okay? It's gonna hurt in terms of computational time because now we are calculating more similarity measures for a pairwise comparison for the same field, but that can be made fast and efficient if we still work within Feleghi-Sonter. Okay? So to show you some evidence that this works, so here what I have done, I have taken data from the Federal Election Commission for everyone that has run for Congress and the Senate from the year 2000 to date. So that's data that is easy to download. What I have gathered from that data is I collected all these individuals, and then I created subsets from that data. So I created a data set that is going to be small or smaller than the other data set that is going to have either 500 observations or 5,000 observations. Then I'm going to create another data set that has 5,000 observations of unique instances of these individuals. I control the overlap. So this is going to serve as a simulation where the overlap is the proportion of records in common that these data sets have. It goes from 10% to 80% of the smaller data set, of course. And then I have the number of the proportion of corrupted names. So it's not the number, it's the proportion of corrupted names, which is going to be within the overlap. It's going to be 10% of the overlap, 50% or 80%. And then to say that this is not the result of a one-off, then I do a Monte Carlo experiment. So I produce 50 data sets per combination of these parameters for the simulations. How do I select which names are going to be corrupted within the overlap? I select them uniformly at random. And what are the type of noise that I introduce? So I'm going to inject deletions, so removing letters, transpositions, moving letters around, keyword typos, replacing an H with a J, and also taking initials. So what is going to be an initial? So it's going to be basically taking the first name and replacing the first name with just the initial. And within transpositions, it's not only transpositions of letters, it's also transpositions of names. So we're going to say first name first, last name second, or the other way around. Okay? Last name first, and then first name second. The evaluation metric that I'm going to use is going to be the F1 score, which is the harmonic mean of precision and recall. So a balance between precision and recall. So let me show you some evidence of that. What I have here, for example, if you were to use just Jarrow-Winkler, you get in this data, which like there is only one field that has been corrupted, which is the name, then you get that basically there is a high F1 score of around almost 80.82. But then if you were to use the aggregation rule, a weighted average based on the entropy of the data, so how much similarity is within the distributions of the similarity measures, then you get an F1 score that is significantly higher, right? And this is true when the level of noise is 50% and when the level of noise is 80%, and when the level of noise is just 10%, basically there is an improvement, but the improvement is not as marked as when you use the weighted, when you use just the Jarrow-Winkler, because in that case, it's just 10% of the overlap. So it's a very small fraction of the observations that have been subjected to noise. And this is noise in just one field. Like I also have simulation results where I inject noise to other fields used for the merge. You can think of the addresses of these politicians. But then you can see like if you move from selecting the minimum of Jacquard, Jarrow-Winkler, and cosine, or if you use the weighted average always does better, and the maximum is actually really restricted, okay? The cut points here are going to be 0.9 for agreement and 0.75 for similarity. To show that the results are not too sensitive for the cut points, another result that I have here is that if you select, for example, for different values of the cut point for similarity, So I varied that from 0.7 to 0.85. The results are basically for 0.75 and 0.80 are basically the same, but 0.85 is the one that maximizes the F1 score. And we fix 0.90 for agreement. And what we move is just we just move the cut point for the similarity level, okay? But where you use one of the two, then 0.75 seems to be the more robust under these simulation settings. What will be like a more principled solution to select the cut points? And in this setting is basically like if you have labeled data, pairs of records for which you know the matching status, it would be to see which one of those maximize the F1 score and then apply those cut points for the rest of the data that is unlabeled. But in the Felegi Center framework, we work only with unlabeled data, okay? So we don't know whom is a match to whom. That's the biggest problem. So this is gonna be a function. So basically fastLink now is gonna give you the functionality that not only you're gonna be allowed to make comparisons using Jarrow-Winkler or Levinstein or Jacquard independently, but you are also going to be allowed to use them as a group. And then you're going to be able to allow where like you want to use disjunctive, conjunctive measures of how to make comparisons, okay? So now let me conclude, like in social science, merging data sets, I'm going to conclude and then I'm going to do through a short tutorial on fastLink, just to give you a sense of how fastLink is used. So merging data sets is at the core of social science research. Typographical errors and noise in the data is gonna make this really difficult. I think employing advanced string similarity measures and aggregation rules is also like a good idea in the setting that in the presence of noisy data, relying just on one similarity measure is, to me, not enough. I think like to where I see the work of fastLink going, and I'm also working on this, is like how can we incorporate human judgment into the merging process? And I have a paper on how to use, for example, machine learning techniques such as active learning, having this iterative process where like the human is providing feedback to a probabilistic model, such that the probabilistic model amends in cases where the probabilistic model is having like lots of trouble adjudicating where a pair of records is a match. So I'm working a lot on that. So fastLink is going to have functionality on that. The paper lays the foundation. Now I'm working on code that is going to allow you within R to have like these very nice, friendly pop-out windows that once you want to label, is going to pop-out window is going to show up, and then you're going to be able to discern if a pair of records is a match or not. That information is going to be passed to the model. The parameters of the model are going to be calculated again. And then you're going to keep doing this process until the predictions made by the model do not change much from iteration to iteration, okay?
Hey, Ted,
Yeah.
that was super interesting. I was just wondering if this was, before you go into the tutorial part, if this would be a good place to ask the question, some of the questions.
Yeah, let's go with that. So let
Okay,
me just
yeah, one,
I just wanted to show you how easy it is to use fastLink. So in the interest of time, I'm just gonna have here in the back end a slide with the syntax, okay? And then we can
oh,
go.
fantastic. This is really the part that I need. And you're going to send me the slides, right? You said?
Yeah, I'm gonna send the slides with you, and then I'm also gonna share with everyone. I'm gonna share with everyone a file that has all the code that is in the slides and the data, so that they can replicate and play with it. Okay, I have
That
prepared
would
that for you
be
guys.
that would be fantastic. Thank you. Yeah, I didn't mean to stop your
No?
tutorial, but I thought maybe it'd be a good spot to ask the questions. So Dakota asked about the EM. he said, is this with the EM running on the hashed groupings or the matching probabilities determined beforehand?
So it's gonna be, so as I try to explain, and now that I have a little bit more time, so the thought exercise is that like we're still going through like the whole sample space per variable in common. So the basic structure of the Feleghi-Sonter model like hasn't changed. Of course, because we are using this locality sensitivity hashing per variable in common, then we are avoiding ex ante to make like some comparisons within that. But now it's based on a probabilistic framework, so it's gonna try to make that more principled. So one way is to get the parameter, like act as if the Feleghi-Sonter model hasn't changed and obtain the parameters of the model, trusting that those probabilities of that the locality sensitive hashing process has worked. Because if that has worked, then the buckets are gonna have just the pairs of records that are really similar, and across buckets, basically the probability of finding a match, an agreement across buckets is gonna be basically 0. So that
Okay.
answers the answer was, but then like it is also true that if you're using the standard blocking techniques where like you subset the data, then what happens in practice is that we fit the Feleghi-Sonter model for each block, right? But then now by blocking and by subsetting, then the parameters of the model change meaning, because now we're feeding different Feleghi-Sonter models, and then we record different set of parameters. So to remedy that and try to keep the problem as one unit, then that's why like I propose this idea of doing locality sensitive hashing within the fields that we use to compare. I think Yves have a question.
Yeah, and before Yves, Jacob had a question.
Okay, let's say.
Uh, let's say, do these approaches generalize to settings in which records are not yet deduplicated within a given data set and where an unknown number of records may correspond to a given individual? How does fastLink handle transitivity in such cases?
So fastLink and the Feleghi-Sonter model, what it assumes is that basically we assume that pairs of records are independent of each other, right? And because pair of records are independent of each other, you can record the coreference, the whole coreference matrix, like the probability that each in the adjacency matrix, the probability that every pair of records is a match or not, right? So then, if you think about it, the Feleghi-Sonter model is built in to do like a many-to-many match. But then there are ways on how to incorporate the one-to-one match. So one idea in Feleghi-Sonter, and to make it more tractable and easier to not to incorporate this into estimation, is to use, for example, linear sum assignment problems, like those that are used in transportation, that you have the adjacency matrix, and then you are just gonna say, oh, like, but in the end, like I believe in a one-to-one matching procedure. So then for every record in data set A, I'm gonna try to find the best match in data set B. So that one idea is all like a greedy algorithm is to find for every pair of records, for every observation in data set A, find the match that has the highest probability in data set B. So that's like a greedy algorithm. A more principled one is to use a linear sum assignment problem, where like basically we have the whole adjacency matrix for all the matching probabilities, and we try to make an optimal assignment so that we try to minimize. We said like everyone should be matched against one, but once I match the first record of data set A to the 10th record of data set B, that 10th record of data set B cannot be matched to any other record in data set A, right? And sometimes that means that not the best match is gonna be allocated to, not the match with the highest probability is gonna be allocated to to any record in data set A. It might be that is the second match. Okay, but this is done ex post. Mauricio Sadinle proposed a very nice idea of like, taking Felegi-Sonter innovation framework and try to incorporate a set of priors over the co-reference structure so that that's estimated within. The only problem is that in terms of estimation, that makes the problems slower. But now Becca Storz and Jerry Ryder and one of their students, they have worked on trying to use the very same ideas, the very same hashing techniques of Felegi-Sonter and apply those to that we propose in fastLink and use that innovation framework. And now they have scaled the method proposed by Mauricio Sadinle. So there is, this is just to say, well, deduplication will be optimal if you have data set that have duplicates. One way to do this is like first you match every data set against itself, and then you just match a deduplicated version of data set A versus a deduplicated version of data set B. And then, but if you don't know, if you don't want to conduct that because the data sets are too large, then you can do a many-to-many match. And in fastLink, that would be to, unfortunately, when we started working on this, and this is one of the things that I need to change in the new version of fastLink, there is this option that is called dedupe. By default is equal to false. By default is equal to true, so that imposes a one-to-one matching. This option should be called one-to-one. If it is false, if you set it to false, it's gonna do a many-to-many match.
Oh, okay. So the way you have it now with dedupe equals false, that's a many-to-many?
If you set equals to false, then it's gonna be, here I wrote it one-to-one. So yeah, it's one-to-one, and then if you set it equal to true,
Oh, true, okay.
it is in the reverse order. So I need to fix this. First, I need to change the name of the argument. It has to be one-to-one. And then one-to-one equal to true. So then we're gonna use either by default, Dakota is asking where we use the linear sum assignment problem. By default, fastLink uses the greedy algorithm because it's faster. So we assign to every record in dataset A, the record in dataset B that has the highest probability of being a match to that record. But there is an option to do the linear assignment problem within fastLink is one of the other arguments. That can also be implemented, but that takes a little bit more time because that is a function that we outsource to our package. And the problem is that those functions they are not highly maintained. So then the problem is that we haven't put that much time into making those. It's a really difficult problem once the data set becomes larger and larger. Doing the Hungarian algorithm on those, it becomes intractable sometimes. So that's why we do the greedy algorithm as a default.
Thank you. Yeah, you're right. I don't know if I think you started reading Eve's question and then
Yeah.
I interrupted you.
No. We can go over Eve's question.
Yeah, I'll let you read it.
So if as fastLink cannot be beaten when comparing two large files if they are entirely in the same block, C++ and OpenMP is as fast as it goes. I totally agree with that. The problem is we still need many blocks for strategical reasons. Some blocks are small, blocking must be done in R, slow, and if the blocks are small, fastLink is no longer multi-threading and loses its comparative advantage. That is also true because fastLink was designed, we always, when we design fastLink was to work within a block, and within a block we parallelize. And we parallelize the operations, and that's where like fastLink becomes faster. But if within fastLink we have calls that if the size of the block is too small, then we don't need to parallelize, because if we parallelize, then by just calling the threads, the multiple threads of the computer, then the problem becomes, it adds seconds to the calculations, and then everything becomes smaller. Another problem with small blocks, and I think like this is also a problem that is faced many times, is for small blocks, the Felegi-Sonter model, because it's based on a small number of pairwise comparisons, then it doesn't tend to perform as well because the parameters of the model, they need to see more agreement patterns for them to, for the parameters of the model to reflect better the data, right? And that's a problem. So then Eve asks, well, based that multi-threading is a promise and blocking, when blocking and you have small blocks is an issue, are you thinking of upgrading fastLink in regard to that issue? So the way that I have been thinking of on how to upgrade that issue is to try to do like the locality sensitive hashing, right? So now the new version of fastLink is gonna be like this. You're gonna pass two data sets. You're gonna pass the variables that are in common between the data sets, which ones are gonna be compared using the string similarity measures, for which one you're gonna do a trinary comparison, agree, similar, disagreement. The cut points for that string comparison by default it uses Jarrow-Winkler, but now fastLink is going to allow you to say, oh, like I want to use Jarrow-Winkler, Levenstein, and Jacquard, for example. You can pass any of 7 string similarity measures, and not only that, there's gonna be an option that is gonna say LHA is equal to true or false. If you want to do locality sensitive hashing, LSH, then what it's gonna do for all the variables that you're comparing using the string similarity measures, is gonna try to construct these buckets. And it's gonna say, oh, like, we're gonna do locality sensitive hashing for those fields. But it's still like the process is the same. We're gonna put them, but all of that is gonna be run in parallel. So we're gonna avoid the small blocks by trying to say, oh, like, hopefully, as I showed in the figure before, to merge two data sets of 600,000 records each. So that means that you don't have to go after blocks. Then it takes, the last time I tried, 15 minutes, right? And this code is a beta version of the code. So I still think that I can do way more to make it more efficient. Again, if for very strategic reasons of your institution, you need to have like small blocks, then I think like it's still like, I hope that fastLink is still gonna run super fast for those small blocks, but then it's gonna lose its comparative advantage. But I'm gonna try to regain that comparative advantage to make you dream that in R you can still do really large data merges, right? So that's gonna be that's sort of the compromise here.
Very, very interesting. Thank you so much, Ted. I don't see any more questions. All right, I'm inspired to really delve into fastLink and I don't know, be dangerous with it. Who knows?
No, you use it and please, if you run into any issues or like if you're starting to use it and then you want some guidance on how to use it, like please feel to reach out. Sometimes it happens that I think like to me like what has been more effective is I'm always a friend of people using fastLink, especially if they work with government institutions and they come and call me and say, oh, like that, like I want your support in this. So sometimes like writing emails takes a lot of time, but I'm more than happy to, what has been great and more beneficial whenever I do this type of interactions is just do Zoom calls and then we go and, well, I never get to see the data. You get to show me code and then I can see, oh, like, I think like you can do this, this, and this. And I'm more than happy to help you brainstorm ideas on how to try to make the most use of fastLink. And,
Well,
and through your mailing list, I'm gonna try to, if it is possible, Wendy, to whenever I make the new release that is gonna incorporate how to make how to use this robust measure of making comparisons using many similarity measures and using three rules, either using different ways of how to aggregate the information. I'm gonna let you guys know about that. The locality sensitive hashing, I think like it's gonna also be part of that. So that my hope is to be done either by the end of this year or early next year to make the new release with those two new features. And then sometime by the next summer to make a release of finally the active learning version of fastLink that allows you to do some labeling and try to fix the mistakes of fastLink. But now you're going to be able to not only use the standard way of doing fastLink, but incorporating the locality density hashing, and also that is going to make the active learning faster, and also the different ways on how to aggregate information from the similarity levels.
Yeah, I thought that was really interesting. Do you have a paper on the aggregation of the similarity measures?
The paper is being written, but right now, like basically, like the
Oh,
paper is a very simple paper where I formalize the assumptions that you need to make for this similarity, for this aggregation rule to work. It comes with some commitments that now it has pushed me to think a lot, and this is what I'm trying to solve. Like the final issue I want to solve with that paper is how to select the cut points, right? I just show you, like, based on simulation or like this, where I know that true matching status, this is the cut point that works best. But trying to think about like how to use the distributions of the similarity measures to try to select the best cut point is where I'm going next. If I solve that issue right away, then that's going to be part of the paper. If not, it's going to be a simpler paper on just the promise of the aggregation rules and the assumptions that we need to make for these aggregation rules to work. Okay.
very, very interesting.
Mhm.
Okay, Ted. Well, thank you so much. I always feel bad about the webinars because we're not in the same room and you can't hear the applause. So
Yeah. Well, thanks everyone, and thank you for the invitation. It has been my pleasure to be here today with you guys.
thank you. It was fantastic talk and lots of good things in the chat. And you've inspired me and I'm sure others. So, all right. Well, thank you, Ted.
Thank you. Have a great day and a
You
good weekend.
too. All right. Take care. Thanks, everybody. Bye.
Bye.